So, so good afternoon, everyone. Welcome to today's live interactive session on geology and soil mechanics. Not geology, sorry, geosynthetic and reinforced soil structures. So, today's discussion there. So, today's discussion also similar to the first discussion was mostly uh, theoretical, right? So in the first week also we started our discussion with some theoretical concepts or the basic theories, the descriptive part from this geosynthetic topic. And today's discussion will be also mostly like that only. And as you might have gone through uh, all your lectures for this week, three lectures in the NPTEL portal. So it's evident that in today's discussion there are not many problems to solve. So what we will be doing is that we will be mostly discussing whatever was discussed in the class, and then what we will do, we will solve some basic problems from, say, our retaining ones. Okay, so discussion will be very simple and easy, not much to solve, not much to do. So it's basic, very basic topic. So our discussion will be very basic. We will keep our discussion very basic, and then in the next week we will see whatever is there. We will proceed that way. But today it's very easy and very simple, straightforward. So we will begin and finish it fast. And in the previous week we solved a lot of problems. So regarding the concept or the main mechanism behind the reinforced earth structures or reinforced soil structures, we solved how the reinforced soil actually behaves, and the what mechanism does it actually follow, right? We studied the failure mechanisms, that is failure in rupture or pull out, all those things we studied. Then we also consequently we solved some problems from that part too. Then we actually saw how to calculate our what to say how to calculate the apparent cohesion and or the increased internal friction angle, all those things we saw, right? And I hope that you were able to actually solve the assignment problems. I hope that you were able to solve the assignment problems properly. And apart from that, one of your course mates actually had one of the assignment problems from the previous week. That problem was actually, just a second, let me just open it here. That problem was, just a second, huh? That problem was regarding where your what to say your uh, in or the your increased circumferential pressure or your minor principal stress. The increased minor principal stress was given, and your friction angle was given. Okay, increased minor principal stress was given and the friction angle was given, and you were actually asked to find out the what the apparent cohesion. Okay, so one of your uh, one of your friends actually asked the question. So I will just share the question with you, and I will just ask you how did you actually solve that. The question was, just a second. Yeah. The question was the additional confining pressure due to reinforcement is estimated as 60 kPa. If the friction angle of the unreinforced soil is 33 degrees, what is the apparent cohesion in the reinforced soil? So this was the question. I will write this down in the chat box also. Yeah. So this was the question. So what? How did you solve this problem? Yeah. What answer did you get, or how did you proceed? You can just switch on your turn on your mic and answer, or you can just write in the chat box also. Anything you can do as per your wish. How did you answer this problem? How did you solve this problem? Additional confining pressure due to reinforcement was given, and the friction angle of the unreinforced soil was given. You were asked to find the apparent cohesion. So how? Yes or no? Were you able to solve it, or did you answer the assignment? Did you attempt the assignment questions? Could you please write yes or no? Attempt the assignment questions or not? No answer. Okay, let it be. I will tell it. So in this question, actually the confining pressure is given, and what your friction angle of the unreinforced soil is given. So this is the very straightforward and easy question. So how we solved it? Okay, how we solved it was actually what we did was we just have to use directly the your Hosen's, for one of the Hosen's, this one formulation, Hosen's equation. So there your sigma r is given. So sigma r is 60 kPa, that is given. So what is the apparent question? The formulation for apparent question is equal to sigma r divided by twice root over Ka, right? Sigma r divided by twice root over K. Okay, so just directly you have to, in the place of sigma r you have to put 60 kPa, and in place of Ka you have to put your 1045 minus 33 by 2, right? 1045 minus 33 by 2, that's all. So directly if you put uh, in place of Ka, if you put not 10, like root over Ka, you directly you put 1045 minus 33 by 2, 60. If you put everything, you will get the answer is, I think, 55 point something. Okay, 55.3 kp, you will get the answer. Okay, this was a very straightforward question with directly just you have to use the relation. All right, so now let us move to the next, just a second. Yeah. So before we begin today's discussion, so very happy Independence Day in advance to all of you. So today is the 11th, and on 15th, that is on Thursday, uh, we are going to celebrate our Independence Day. So wishing everyone a very happy Independence Day in advance. And so on this note, we begin today's discussion. So the first topic of discussion is why do we why do we need retaining walls? Okay, why what is the need of retaining walls? Why do we need retaining walls? Okay, so that is the first question. Why do we actually need retaining walls? Yeah. So what is the need of retaining walls? So retaining walls are actually uh, used to what support the soil wherever the soil is say, or the support the slope where the slope is say too steep, okay, too steep, or the strength of the soil is too low. So in that cases what we do, we need to use retaining walls to support the soil, right? So that is the main purpose of main purpose of retaining walls. Okay, so what, so soil has what, soil has high compressive strength but limited tensile and shear strengths, right? So soil has high compressive strength but very limited tensile and shear strength. Okay, just give me a second. Yeah, sorry, I just got a call actually. Okay, so it has limited tensile and shear strength, right? So it can stand on its own up to its angle of repose. The angle of repose actually for granular soils, angle of repose is nothing but it is equal to the what, angle of interpretation. You take sand in your hand and you start drop sprinkling it from a height. So what will happen? Gradually it will form a heap like this, heap of sand like this, right, over the ground. So this angle is nothing but the angle of repose. Okay, or this angle is nothing but the angle of repose. So this angle of repose is generally equal to,
Ashish,
yes,
excuse
yes,
me.
yeah,
Your voice is breaking. Keep breaking.
probably because there is some maybe internet issue.
Still, I can't hear you.
Yeah, now can you hear?
Yeah, a bit.
Okay, 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 but I have no option. Now is it audible?
Yes.
Okay, 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 okay. So what I was saying is that the if you take sand in your hand and you drop it, it will follow. It will make a this heap, right? This heap of soil will actually be inclined at the angle of internal friction or the angle of repose. But what if you want the soil to have a steep angle? Okay, like if you want the soil to rest instead of like this, you want the soil to stand like this. So soil cannot stand on its own in this angle. So what, it will fall. So to prevent this, what do we use? We use retaining walls, right? We use retaining walls. So this is why retaining walls will be used.
Ashish, one more question.
Yeah, yeah, yeah,
What
yeah, yeah.
angle, more than what angle it goes for a retaining structure?
Yeah, that I think it was discussed in the class. Probably, if I remember, it was around uh 7
45,
60 or 70
45
degree, I
degree?
think. No, more than that, I think. I have to see actually. I will check and let you know. One
Okay.
sec. Okay, okay, I will check and let you know. Yeah. So next we have the type of retaining walls. Okay, so now first we saw why do we need retaining walls. Retaining walls are needed to actually resist the soil. Say we have steep slope, to resist the failure of that steep slope we need to prevent the failure of the steep slope we need retaining wall. Okay, now the types of retaining wall. Okay, so the most common and the most basic type of retaining wall is our What gravity retaining wall? So gravity. So can you tell me how these gravity retaining walls are actually made? Are these RCC structures or these are just concrete structures?
We can make through geocell also, right?
Yeah, that also we can do. That also we can do, but that will be your reinforced kind of reinforced soil walls. Okay, so the main basic initial what retaining walls is to be made, those were our gravity retaining walls. So this is our gravity retaining wall. So gravity retaining walls are how our gravity retaining walls are made. These are just normal plain concrete structures. Okay, these have no reinforcement, just the main mechanism with which it resists the lateral force of the soil is its weight. Okay, so it has a large weight, large self weight, and due to that weight actually it resists the lateral lateral earth pressure. Okay, so that is the main mechanism of our what mechanism of our uh, gravity retaining walls. Okay, gravity, the weight is the main resisting force. Okay, uh, after that we have the cantilever retaining wall. So these are actually cantilever retaining walls. So cantilever retaining walls are RCC structures, right? These are RCC structures. So we have the main found base or the foundation of the retaining wall, we have your reinforcement here, and then we have the cantilever portion, right? We have the cantilever portion. We have the cantilever portion. So can you tell me why the generally in cantilever retaining walls the top portion is tapered? Why is the top portion tapered in cantilever retaining walls? Very basic question, right? Why is the top portion tapered?
Our pressure is less. Active earth pressure is
Yeah,
less.
earth pressure is just, but if you consider in terms of moment, where is the, see, if moment is resisted maximum here, right? And as you go away from the support, your this moment actually bending moment actually reduces, isn't it? So that's the main reason, right? So you have lesser bending moment at the edge. And yeah, so there are some parts. So this part is actually called the toe, and this back part is called the heel of the retaining wall, heel of the cantilever retaining wall. And also sometimes we use a sheared key at the bottom, and what happens is that that sheared key actually also prevents resists the sliding. So due to this lateral force, there is a tendency for the retaining wall to slide. So to increase the sliding factor of safety, what we use the shear key. So the shear key, what happens, there is some passive resistance of the soil that develops here at the shear key. Okay, so due to that, what happens, the factor of safety for sliding increases more. Okay? This is the main use of shear key. Okay, so now what is next? Mm, hmm. Yeah, so if I have a say cantilever beam, okay, if I have a cantilever beam with a UDL, say UDL. So can you tell me how will be your the shear force diagram and the bending moment diagram for this cantilever beam? How will be the shear force diagram and the SFD and the BMD shear force diagram and the bending moment diagram for this cantilever beam? So we have fixed support, we have this beam, and we have a UDL, say W. Okay, so how will the SFD and BMD be, if you remember from your basic strength of material course or the basic structural mechanics course, structural analysis course? What is the SFD and the BMD of a cantilever beam? So if you have a cantilever like this with UDL, the SFD is going to be somewhat like this, right? Right, somewhat like this. This is the SFD. And how will be the BMD, bending moment diagram? It will be something like this, isn't it? Something like this, right? So you can obviously you can see that at the tip your bending moment is actually low, right? And at the where you have the fixity, you have high bending moment, right? So that is the reason you have the width of the section is higher towards the bottom, and as we go up we can actually reduce the section size, okay, because the demand of the bending moment is actually low. Okay, the demand is actually low there. Okay. Yeah. So now similar to that, we have some more types of retaining walls. So we have counterflow retaining walls. Counterflow retaining walls means it's similar, but say if you want to construct very high cantilever retaining walls, so with the height you want to construct it very high. So so to give that give the retaining wall more stability, okay, so just give it as support. What we do, we put some counter forts like this, okay, like supports. We put some supports, on the retaining wall, okay, like this, some supports on the retaining wall. These are nothing but the counter forts retaining wall, okay, these are nothing but the counter fort retaining wall. And can you tell me what is this here? What is this image here? What is this? What are these things? Do you know? What are these? What are these? What are these called?
Geomembrane.
No, no, these are not geomembrane. See, very tight properly. These are steel, made up of steel.
Shuttering wall,
What? What?
shutter,
These are not shuttering. These are something else.
Corrugated sheets. Steel corrugated.
Like that only, similar to that, but uh, so see, where do you generally see this type of structure? Where do you have to use?
tanks,
Where?
tank,
Tank? Not tanks.
Is it well foundation? Something like that?
Yes, like yeah, like that. Not well foundation. These are something else. So uh, these are actually called sheet piles.
Okay.
Sheet pile. Okay, these are actually called sheet piles. So so these are made of steel, and what we do, we actually drive them into the soil, okay, drive them into the soil. And those actually, these are like this, okay, these are like this, actually like vertical like this. And what happens, these get interlocked with each other, okay, these get interlocked with each other. And what we can do, these are very heavy, and what we can easily drive them into the soil, okay. And if you drive them into the soil, and say if you want to construct, so generally in bridge construction, okay, you want to construct a bridge over a river, Okay, so how do you there are many processes with which you can actually what you can do, you can construct the pier. Okay, the pier, so water you have to, somehow you have to arrest the water, right? Arrest the water so that you can construct the pier. In that case, what we do, we drive the sheet piles. Okay, we drive the sheet piles into the river bed, and then we pump the water out. Okay, pump the water out, so inside we get a dry environment, and then we can construct, we can do the piling, and we can then start constructing the pier of the bridge. So these are sheet piles actually, and these sheet piles in this image, whatever you can see, this is actually used as a braced kind of retaining wall. Okay, this is uh, used as a braced retaining wall. Okay, braced retaining wall, it is used in that purpose, for that purpose it is used here. But your shear sheet piles are generally used to make coffer dams. Okay, coffer dams for the construction of piers in river. Let me show you a video, then it will be clear. Let me just open a video how these sheet piles are actually used. Let me just show you sheet. Yeah, so these are called sheet pile cords. So see this video. So you can see these are very heavy big type kind of structure. Okay, and these are driven into the soil. This video is not clear, so these are driven into the soil.
Hello, to prevent the backfill entering into the excavated portion. It gives the heat piling, so here it is. In this video, we will restrict ourselves to explain what is sheet piling. That's it. The different types of sheet piling will be in the coming videos. So, what is sheet piling? It is nothing but sheets of steel. The sheets of steel are driven into the ground to prevent the backfill entering into the excavated portion. It gives the stabilization to the backfill. See, this is the place what we need to do construction. So we excavated this place and we filled it here. This is the backfill. So we don't want this backfill to come into this place. So what we do is a retaining wall like structure. What we do is we do sheet piling. This kind of interlocked sheet, steel sheet mechanism are driven into the ground. So this will prevent this backfill.
Your voice is not audible.
Yeah. Hello. Yeah. Sorry. And just a minute. I will just stop and reshare this one. Just a second. Yeah. So what I was saying is that, so these are heavy steel structures. Okay, steel, these plates, or not plates actually, some interlocking structures that are driven into the soil. So here you can see that here we have some backfill soil. Similarly, this side also you have backfill soil. This side also you have backfill soil. But what we need, we actually excavated this portion. Okay, this portion, and we don't want this backfill to actually come and block our main construction. So we say we want to construct something here. Okay, so we want to construct a footing here, but we don't want this backfill to interfere in our construction, right? So what we did, we inserted the sheet piles. We made a coffer dam like structure, and we inserted the sheet piles all around. And these sheet piles, to give more support, what we did, we braced these steels with sheet piles with some bracings also. So these are the bracings. Okay, to further support the steel sheet pile, was what we did, we use some bracings also. So first we drive the sheet piles, then also we, for some more support, what we do, we use some bracings. So now what will happen, whatever force this backfill is offering, putting on this sheet pile, it will be able to resist easily, and we will be easily able to carry out our construction activities in this place. Okay, so this is the main purpose. So this is also type of a retaining structure, isn't it? So it is retaining the soil, so it is also a type of retaining structure. Okay, so here are some more types of retaining structures. You can see that is the anchor sheet pile. So same sheet piles, we have driven the sheet piles here. Okay, made the sheet pile wall by driving the sheet piles into the soil. But here, what, instead of using bracings, what we did, we have used some anchors. Okay, we have used some anchors. So these anchors are actually what, holding the sheet pile back into the soil. So there, if the sheet pile tries to move away, if the sheet pile tries to move this side, what will happen, some passive resistance is actually developed here at the anchor. Okay, at the anchor, which actually prevents the sheet pile to fall around or collapse. Okay, these are anchored sheet piles. Okay, similar to the previous photo whatever says, so these are the brace sheet piles. So here bracings are used like this. Okay, here you can see, so we have two sheet piles, and with these struts, what you are doing, we are bracing the sheet pile. Okay, you are bracing the sheet pile so that it does not cave in, the sheet pile does not cave in. What you are doing, we are using some bracings in between. Okay, yeah, yeah. Now more types of retaining wall. So the main type of retaining wall that we'll be designing, that is our reinforced soil wall, right? Reinforced soil wall. So in that case, what do we have? First we have the reinforced soil section and our backfill section. Okay, the reinforced soil section means the soil section where we have used some kind of reinforcement. Okay, it may be geogrid reinforcement, it may be geotextile reinforcement. Okay, it can be any type of reinforcement. That part is known as the reinforced soil, and the part which is not reinforced, it is nothing but a retained soil, or just the backfill soil. Okay, the backfill soil. Now in this front part, this is known as the facing. Now this facing also can be of many types. One of the types of facing is actually shown here. That is the use of modular bricks, modular blocks or modular bricks. So modular blocks are nothing but brick-like structure like this. Okay, some brick-like structures that are actually placed one above another. Okay, to form just the facing of the wall. Okay, just to form the facing of the wall. This is the modular blocks. Then we have some more types like this complete rigid facing wall. Okay, it's rigid facing wall. You have the whole length of one rigid facing wall, and then we have this geosynthetic attached to it like that. Okay, then we can have wrap around reinforced soil walls, wrap around it. So where we use geotextiles to reinforce the soil. So you will just use the geotextile. So you have one layer of geotextile, you fill the soil, then you put one more geotextile, you fill the soil, one more layer like this you just wrap it around. Okay, wrap around structure. Okay, we will see that, we will solve some problems also later. So we will see this will we will be able to clearly visualize that. Okay, so this is the one thing. Now one more way is by the nailing of the soil. Okay, nailing of the soil, this soil nailing you must have encountered while traveling in the highways, or sometimes in your own city nearby areas where construction. So many railway projects near the railway lines, generally nowadays Indian Railways are doing most of the construction where they have to retain the soil. What they do, they nail the soil. Okay, that they nailed us. So soil nails are literally nails only, like nails, like thick, big rods that are drilled into the soil. Okay, drilled into the soil, and then it is locked like this at the surface. Okay, it is locked like this at the surface. Okay, so these soil nails actually also help to resist the failure of the retaining walls or the slopes. How it resists the failure of the slope? So you can see here. So here we have a slope, right? Here we have a slope, and say this is the failure zone of the slope. Thus if you do the slip circle analysis, you will see that this is the failure surface. So that means the slope will tend to fail along this surface. Okay, the slope will tend to slide out along this surface. But what if we use some soil nails? The soil nails, what will do? The soil nails will actually nothing but anchor this failure zone with the backfill or with the virgin soil that is behind that. So in that way, it is going to prevent the failure of that failure slice to come out. Okay, that way it is going to prevent the failure slice to actually fail. Okay, the probable failure slice to actually fail, it's going to prevent. So these are various types of retaining structures. Okay, so as I said, there are many types of facing. So you can see precast facing panels are used like that sometimes. Okay, then we have a long rigid facing, and which might be anchored also at the back. So there are various types of actually facing that can be used. Okay, it depends upon the project and whatnot. Okay, now let us see this video once. Okay, I will play this video. So this is a video on the soil nailing. Okay, how the complete soil nailing process is actually explained here. So if you see this video, it will be very clear to you. Okay, so please see this video. Okay.
Soil nail is a soil reinforcement technique used for protection and stabilization of natural or excavated slopes. The technique improves the overall stability of in-situ slopes and restrains the slopes from failure. The technique also has advantage of strengthening the slope without accessing earthwork to provide construction access and working space either for permanent or temporary purposes. First thing first, the position of soil nails in a grid pattern are to be set out. So we have to ensure that the horizontal and vertical spacings are correct, and the inclinations and the angle of inclinations are also checked during the survey. Then we mark the position with pegs. Typically, the spacing of horizontal and vertical of the soil nails are 1000 to 1500 mm, while the angle of inclinations are 15 to 35 degrees. Then the drilling machine will be mobilized to the soil nail position. The drilling rod is then positioned and adjusted to the specific angle of inclination, which is as mentioned 15 degree. Then the operation of drilling will be started, and at the same time the drill soil will be flushed out by air. Here we can see that the air is flushing out the soil during the operation. And this is how the machine, which is called the leader, have multiple pieces of extension that is used to extend the drilling rod manually. The video shows when it's done drilling, the workers are pulling the extension out one by one manually. Then, the steel reinforcement, which has a size of typically T20 to T32, has a length of 12 meter, will be inserted into the drill hole. Then the grout will be pumped into the drill hole from the bottom of the drill hole. This is also to ensure that the soil at the toe level of the drill hole will be flushed out along with the grout to ensure the soundness and quality of the grout used in constructing the soil nail. The installation process of other soil nail at other positions will be repeated until the entire slope is completed. Then a gunite wall will be sprayed as per required in the construction drawing. Upon completing the gunite work, base plate will need to be installed and locked off. Then, we will prepare the formwork mold and top out with cement and sand mix to construct the soil nail cap, which will look something like the second picture, in which I will show in a second. Now let's move on to modeling and analysis. The model shows a slope that is without reinforcement. According to the slope stability analysis software, the factor of safety of the critical slip surface is 0.606, which is actually lower than 1, which means it will be very likely to slip off. After adding soil reinforcement to the slope, the factor of safety for the most critical slip surface is 1.618. This shows that the slip surface will be unlikely to slip off. The factor of safety is also satisfactory according to the design code. From the local practice, the soil nail diameter are typically 100 to 150 mm, but the steel reinforcement ranges from T20 to T32. The spacing of the soil nails are typically 1000 to 1500 mm center to center with a typical inclination of 15 to 35 degrees. We have built a slope that is similar to what a real-life slope would look like using soil, and then we place some weight on top of the soil until it collapses. In a few seconds, we can see from the side until a certain weight was added, which is about 26 kg according to our estimation and calculation based on the amount of paper and its unit weight, the slope became unstable and started crumbling down. Apparently, the slope hasn't even moved a little bit even after the same amount of weight is placed on top. Therefore, we try to put more weight on top and see how much weight it can sustain before it fails. Unfortunately, before the slope collapsed, our piles of paper which were not evenly placed on top has caused the paper tower to fall. However, from the side view, we can see that even when the piles of paper and report has fallen, the slope was sturdy and does not even move an inch. Alright, I hope you find this video helpful for you to understand soil nail and its purpose better. Thank you for watching.
Yeah, so you understood, right? The whole process, how it is actually used. Right, so first what we have to do, we have to drill the wall, so drill the hole. Okay, we drill the hole, then we put the steel reinforcement into the soil wall or the soil slope. After that, what we do, you put our cement grout in it, the cement grouting, the cement mixture, what we do, we put in it so that it goes inside, fills the gaps and holds the reinforcement in place, right? So we grout the hole wherever you have put the reinforcement, and after that what we do, we actually put a, sometimes what we see here, you can see some mesh kind of structure, like so this some mesh kind of thing you can see here, right? So generally this is the practice. What we do, we put some net steel meshing, steel net kind of thing, then and over that we put this capping. Okay, we put this capping, And the last step is going to be the shotcreting or gunneting. You know what shotcreting is, right? Nothing but spraying of concrete. That is called the shotcreting. So what we do is shotcrete it. Okay, shotcrete the whole surface. Okay, so this completes the whole soil nailing process. Okay, and in the video also he clearly, like, very properly explained everything, right? So you saw the experiment, this small demo whatever they did. So initially without the nails, the slope was taking lesser load, but when he actually put this wooden nails in the demonstrate the model, in his model, a large amount of load that slope could take, the same slope could take, right? So this is the main use of soil nails. Okay, the soil nails are used for this your slope stabilization. Also it is used for to reinforce the soil. Say you have a straight what to say, you have somewhat vertical, like more steep. So here whatever you are seeing, it is quite inclined, right? Say you have more steep kind of soil, in that case also this soil nail actually works many times. Okay, so this is the main process and how this soil nail actually behaves. And you asked me the question that uh, uh, what is the angle above which we have to use we have to construct a retaining wall. So that angle is generally not fixed, right? Because it depends, totally depends upon the property of the soil, the cn 5 value of the soil, isn't it? The mostly the 5 value of the soil. Say if that soil in that place, whatever soil you have, that soil is having very low friction angle, and obviously that soil is going to have very low strength. And that case, maybe 45-degree slope also won't be stable enough, isn't it? So that is the case. So we cannot there is no definite number that above this angle you have to use retaining wall, and below this angle it is uh, you can have a slope. Okay, so that is the thing. Yeah. So this figure, whatever you are seeing, the first figure, this figure we actually already saw in the previous class, right? So as the reinforcement or as the number of layers of reinforcement in the soil increases, the strength of the complete reinforced soil increases, right? So for unreinforced soil, we have this, and for the soil with 5 layers of reinforcement, we have this curve. So clearly we can see that very high amount of load the reinforced soil is able to take. Okay, so what are the observation? Higher strength and stiffness for reinforced soil. More reinforcement gives higher strength and stiffness. All show. Now one more, in the previous class also I asked this question. Okay, now in this class also, this today's session also, I will be asking the same questions. Please see the third point. All responses show similar all responses have similar behavior at low strains. So why is it, why does it have similar behavior at low strains? So in this graph, if you see, initially at very low strains, all these responses, all the responses, whether unreinforced or reinforced, have the same behavior, right? At low strains the responses are very similar. Okay, why is it so? And as strain increases, these responses differ. So initially, why at low strains the responses are similar? So this is the question. Why at low strains all the responses are similar? Yeah. What is the reason for that, reasoning for this? Why at low strains the behavior is similar for both unreinforced and reinforced soil? What is the reason? I told this in the previous class also.
Interaction between soil and the reinforcement Impacted.
What interaction? How does the interaction behave when the strain is low? Try. It's easy, very easy. Just try to answer. Just try. Whatever is coming, whatever you are able to think intuitively. Try to answer that. So why is this? Why is that? Think about in terms of load. What is happening? So when the load is, yeah, what?
The soil is good in compression as it is. It's only when it crosses a particular limit, then the tension limit, when it comes to that particular point, the additional reinforcement takes over, and the soil, it crosses the minimum tensile carrying capacity of soil. Only then the reinforcement starts acting role. So in the initial part of the load, the soil has still got a little bit of minimum tensile which it can tolerate. Beyond that, only the reinforcements are coming in.
So the thing is nothing that technical. It's very simple, right? You have to think very simply. The answer is very simple, right? Why is it happening? Because the soil, because at that time the soil itself is only taking the load, isn't it? Right? The soil is taking the load. That load is not yet transferred to the reinforcement. Why is it not yet transferred to the reinforcement? Because the strain mobilization has not yet occurred in that reinforcement. For load to get transferred to the reinforcement, what has to happen? There's some strains are have to get generated in the reinforcement, right? Some strains are have to get generated in the reinforcement, or at low strains, what low load, that low load or low axial strain, whatever, that strains are not yet mobilized completely, that strains are not yet transferred to the reinforcement, right? That's why the mobilization of the strength of reinforcement is very less. The strength is not yet mobilized, strength of the reinforcement is not yet mobilized. So as you increase the load, the strain increases. As more and more strain keeps on increasing in the reinforcement, the mobilization of the load carrying capacity of the reinforcement happens. Okay, then it starts taking the load. If the strain only does not mobilize, it means load transfer is not happening, and load transfer has to happen when there is strain mobilization. So when the strain is very low, the strains are not yet mobilized in the reinforcement, right? So that is this. Okay. Kenya soil doesn't have tensile strength. No tensile strength. We do not consider soil as a tensile in this case particularly. We consider it is only having compression. Generally, we do not tend to, when we explain these things, it has some tensile, very minute. So we generally tend to neglect that tensile. Soil does not have any tensile strength. Not that it is not that soil is taking some tension at the beginning, and after, when it is not able to take the tension, it is getting transferred to the soil. Not that, but what is happening is that the enough strains are not getting, strain is not getting generated in the reinforcement itself. That's why this load transfer is not happening. That is the reason. Okay, so I was mentioning there are different types of facings that we can have. So one is the full height panel. Okay, the rigid full height panel. So this is one whole complete panel. Okay, this does not have any breaks in between. One whole complete panel is there. Okay, one whole complete panel, and to that panel we have the reinforcements attached. Okay, which is the full height panel. Then we have the segmental panel walls. So here we have some segments that are interlocked with each other. Generally we tend to use this only, segmental panel walls. Okay, generally we use this. So we will see that. We will see one video also, very good video, very excellent video, where they have shown from the scratch how a reinforced earth wall is constructed. Okay. Then we have modular block face walls. These modular blocks are nothing but brick-like things. That photos you must have seen during the class. Brick-like things, where these bricks are actually placed, and over that we layer by layer we actually put the reinforcement. Okay. And last type is the geotextile wrap retaining wall. Okay, where there is no facing, but the geotextile that they are using for the reinforcement, that only we are wrapping around. Okay, that only we are wrapping. Yeah. So what are the types of reinforcement? What are the types of reinforcement that we can have? What are the types of reinforcement that we can have? This we have been discussing since the first class, first discussion session, right? So what are the types of reinforcement that we may have? What are the types of reinforcement? What can we use here? What are these? What these can be? What these reinforcements can be? What are the types of reinforcement? What are the various types? What are the types of reinforcement that we can have? That is the question. You already know. What is this? What are these? What are these reinforcements?
Steel reinforcement.
Yeah, steel reinforcement one. Then let me write it down. You said steel. Yeah. Then
It can be made of geocomposites,
not geocomposite. Something
polymers,
else. No,
geopolymers,
no. Not. I'm just asking the type.
nets,
What are the?
geonets,
Huh?
geonets,
Not geonet.
geonets.
No, no, no. Geonet is used only for drainage. Geo what? Which geosynthetic will you use for reinforcement? Which geosynthetic has this serves the function, has a function of reinforcement? Tell. You know already. Please tell.
It is not
Okay, what are the types of geosynthetics? Forget about it. What are the types of geosynthetics?
geotextile,
Geonet.
geogrids,
Yeah.
geonets,
Geotextile.
Yeah.
geogrids,
So out
geonets,
of this,
geomembranes.
yeah. So out of this, which will you use for reinforcement?
Geotextile.
Yeah. Geotextile and
Geogrids.
yeah, correct.
Geocells.
Geocell, yeah, but mainly for reinforcer. Geocell also you can use. Yeah, geocell also you can use, but mostly we use this geotextile and geogrid. Okay, geocell also you can use. Directly we can construct walls with the help of geocell. You're right. Geocell also we can use, but mostly when we say reinforced soil walls, the thing that should come to our mind is geotextile and geogrid. Mostly geogrid. Okay, mostly geogrids. Okay, now which type of geotextile you will use? Non-woven or woven? Which type of geotextile will? Yeah, woven geotextile. Yeah, correct. Woven geotextile. And what are the types of geogrids that are available to us? What are the types of geogrids?
Biaxial, triaxial,
What? Biaxial and
triaxial, uniaxial.
no, biaxial and uniaxial. These are the two
Triaxial is there.
directions. Yeah, biaxial and uniaxial. Right. Main types. Whatever that are used. And then what are the types of steel reinforcement that we can use? What are the types of steel reinforcement that we can use?
Is it
Geocell
Gabion?
is no, not gabions. Just form of steel reinforcement. I am asking. In what
Like
form do we use?
stainless steel, carbon steel.
We can use
Yeah,
them as
steel what? Steel strips, right? Strips.
yes.
Yeah, we can use them as steel strips. Like these strips we can use, and we can use steel
Coils.
meshes.
Steel meshes.
Yeah, steel meshes, right? Okay, so steel reinforcement we can use steel strips, steel meshes. Okay, function or where you want to use the design, and you can also use your geocells to construct
Sir, can't hear you.
reinforced soil.
Ashish can't hear you.
Yeah, now.
Yes.
Yeah. Okay. So what I was saying is that yeah, we can use steel strips, steel meshes, then woven geotextiles we can use. Then we can use uniaxial or biaxial or triaxial geogrids depending upon the design and use. And also we can use the geocells for directly constructing reinforced soil walls. Okay. Now what are the possible wall configurations that we can have? Yeah. Now we can hear me,
Ashish,
right?
we can't hear you.
Please tell me. Okay. Sometimes
We can't hear you.
yeah.
We
Please
can't hear
tell me.
you.
Okay. When now you can hear me, right?
Yes, please.
Yeah. Whenever it goes, now please let me know because this connection sometimes goes. I don't know what is the problem with this. Please let me know whenever you cannot hear me. So yeah, so wall configuration. What are the wall configurations? Nothing means how shall we actually have the layout of the this reinforcement. Okay, so one is what. So let's say you have this wall. We have the reinforced soil, and this is the wall facing, and you can have the reinforcement like this. Okay, equal reinforcement at all heights. Then you can have like this, or you can have like this, or you can have back to back walls. Okay, back to back walls like this. So these are the some of the basic wall configurations we can have. So we will see later how to how this length of reinforcement, how this length of reinforcement is actually decided, that we will see. Okay, we will solve problems later in this course. That time we will see that how this length of reinforcement is actually decided. So these problems will be very interesting and easy, very easy, a little bit lengthy but very interesting also. How do we decide all these things? How do we decide the length of the reinforcement? All these things we will solve. All these problems we are going to solve later in this course. Okay. So now, what are the main components? Okay, what are the main components of a reinforced soil wall system? Okay, reinforced soil retaining wall system. What are the main components? Okay, so you will tell me. I will just draw a rough diagram. You are going to tell me what are the components. Yeah. So what is this? What are these? Just now we discussed. What are these? called?
Facing panels.
Yeah, facing panels. We facing panels or say blocks of facing panels. Okay. Now, what is this?
Reinforcement.
Yeah, reinforcement. Then what is this whole part called? This whole region, what is this called? This whole part, this whole region, what is this part?
Active phase.
No, this is not the active phase. Hold this
Backfilter.
part. This is the backfill. The backfill soil. This is the reinforced soil, right?
Okay.
This is the reinforced soil. Okay. What is this?
Foundation pad, we can say.
Yeah, pad. Some pad, not foundation pad. Some other name. You will know if you have done the lecture. You will know that. What is that? What pad?
Leveling pad. Leveling pad.
Level. Correct. Leveling pad. It's the leveling pad. And why is this leveling pad actually used? Why is it used?
To give us some sort of stability to the panels.
Yeah, just to have a level surface. Okay, generally, just rather than keeping this panel being rest over the soil directly, just to have a strong, hard, level surface, we have this leveling pad. What is this leveling pad made up of? How do we make this leveling pad?
It's also made of concrete, some blocks.
Yeah, concrete. What concrete? Reinforced concrete or plain concrete?
Yes, plain concrete.
Yeah, plain concrete. PCC. Okay, and what is this? This soil, what is this soil called?
Subsurface.
Foundation. Yeah, foundation soil. Right?
Foundation.
Okay. Now next we will see a video by Strata. So Strata is a company you all know that who has this geosynthetic products, and they design these geosynthetic structures. So we'll see one video from Strata where they have used, we have completely shown the process from the start to the end, how this reinforced soil retaining walls or reinforced soil walls are constructed. Okay.
Strata. With eyes on innovations, we have developed a patented systems for panel walls. Strata Wall EC is a concrete panel-faced reinforced soil wall system. The granular backfill is reinforced with strata strip geogrids to create an internally stabilized mass of reinforced soil. Strata strip is positively connected to the panel. Internally stabilized mass of reinforced soil.
So whatever they are using here, whatever they are using here, that is actually geogrid strips. Okay, geogrid strips. Okay, so these are what is the geogrids, but these are like this. Okay, geogrid strips. Okay, like this geogrid strips they are using for reinforcement in this video, whatever they are showing. Okay.
Strata strip is positively connected to the panel. Bypassing it through Strata Connect, embedded connectors which create a cavity in the concrete panel. Strata wall embedded connectors consists of strata strip geogrids, which are made from high tenacity polyester yarn and are coated with a proprietary saturation material. Strata Connect are connectors that creates C-shaped cavities within the concrete panels. Strata Connect is designed to allow easy access for the strata strip reinforcement and precast concrete panels. Strata AC wall systems adhere to highest design safety standards.
These you can ignore. They are just promoting their product, so that part you can ignore. Just focus on how they are using how they are the construction process. Okay, just focus on this part. This add part, whatever they are doing, that you can ignore for now.
It is economical and is approved by IIT Madras, backed by Strata's assurance on quality. The Strata Connect inserts must be placed in position within the assembled cage and tied to the vertical bars with binding wire. The surface of panel mold has to be perfectly leveled. Correct positioning and fixing of connector on the reinforcement must be rechecked. The reinforcement cage with the connectors will be held in position using channels and S-hooks. Concrete is placed in the mold with proper vibration. Necessary precautions must be taken to ensure connectors are in place and properly protected. Tapes protecting the cavities of the SC connectors shall be removed 6 hours after casting. The cavity of all the connectors should be checked for any blockages. Lifting straps are placed through the SC connector cavity and are lifted with an overhead crane or a low-capacity tire-mounted mobile crane and carried to the area designated for curing. The panels are then covered and sprayed regularly with water or through steam curing. Excavation of the ground should be done up to the foundation level as indicated in the drawing. The foamwork for the leveling pad shall be fixed and concrete shall be placed within the foamwork. The vertical direction and longitudinal alignments shall be continuously checked. Strata wall.
So what I was trying to show there was that you saw how this leveling pad was constructed, right? So they just poured the plain concrete there, and over that they are starting to place the facing wall. Okay, so they how they constructed the leveling pad? That they made the first they uh, cleared out the portion of the soil at that place. They leveled it, and over that they poured plain concrete, and then they constructed the leveling pad. Okay, let us see.
The foamwork for the leveling pad shall be fixed and concrete shall be placed within the foamwork. vertical direction and longitudinal alignments shall be continuously checked. Wooden wedges are used to align the panels in position and ensure that they maintain the correct line and better. Wooden clamps are used for holding the panels in an upright position. Watering and compaction is carried out till the soil reaches.
This is also very important. You saw that they have put some white, they have pasted some white, see, they have pasted this white, what to say, uh, thing right here. So can you tell me what are these? These are non-woven geotextile. Why these non-woven geotextiles are fixed here? Can you tell me? Why they are sealing the gaps with this non-woven geotextile? Why are they sealing the gaps with the non-woven
Protect the
geotextile?
sand.
The fines should not
What-
escape.
Yeah,
Fine
correct.
sand should be.
Yeah, the backfill, whatever soil, whatever sand we are using there, it should not come out. Okay, it should not be lost. That's why you are using this as a filter here. Okay, the purpose of the non-woven geotextile here is filtration. Okay.
Watering and compaction is carried out till the soil reaches required density. While a vibratory compactor shall be used to compact the soil matrix, only hand tamping with a light mechanical tamper shall be done within 1 meter of the panel.
This is also very important, the compaction process. So when you compact it in layers, the roller should always be parallel to the along the length of the wall. Okay, it should never be like that towards the panel of the wall. Okay, the rolling or the compaction should never be towards the wall. Okay, else your wall is going to, these facings are going to fall down. The wall, you won't be able to construct the wall. Okay, initially also from the starting scale, if you roll it in the other direction, whatever is shown here, perpendicular to that direction towards the wall, if you start compacting it, what will happen? The vibrating force or the compacting energy will get transferred to these facing walls, and these facing walls will actually fall on the other side, or you are going to have some deformations that will get developed. Okay, so we do not want that. So always the rolling or the compaction should be in parallel it should be done. And this rolling and near the facing panels, always hand vibrator should be used. Okay, never to use the roller should not be taken very close to these panel walls. Okay, this is also very important.
Strutter strip reinforcement strips are inserted in the panel. The strips shall be carefully rolled and placed near the respective panels. The strips placed during the process must be in perfectly taut condition. Plinth protection to be added outside the wall to protect against carver, rodents, etc. Approved geocomposite should be placed next to the panel fascia above ground level as per the drawing.
Now what is the purpose of this geocomposite?
It will allow only the draining of the fluid
Correct,
and not
correct.
the fines.
Correct. Drainage is the main function of the geocomposite here. The geocomposite, why we are calling it geocomposite here? Why are calling it geocomposite?
It's the filtration medium.
No, why geocomposite? Why composite?
Lateral drainage.
No.
It's made out
Correct,
It's made
correct.
out of this one textile,
Geotextile and two types
non-woven,
of.
non-woven, non-woven.
It is called geocomposite because it is made up of two type of geosynthetic. One is your non-woven geotextile and also geonet you are using. So see this. See this. It is a sandwich kind of thing, right?
The geocomposite should be placed next to the panel fascia, above ground level, as per the drawing.
See, got it, right? It is a sandwich kind of thing. One layer of non-woven geotextile, then we have geonet, and over that we have your again we have the geotextile. That's why it is a composite of two types of geosynthetic. That's why it is known as a geocomposite. And this geocomposite will act as both as a filter and a drainage. Like it is going to prevent the fines to enter. It is going to allow the water to enter, and then along this vertical direction the water can easily flow in plane permeability, right? Water can easily flow and drain out. Okay, so the main purpose is drainage. The main purpose of the geonet is the drainage, and the geotextile that is used at the top and bottom, the sandwich, the top and bottom, the main purpose of that is filtration. Okay.
Coping beam connecting all the top panels shall be casted. Strata wall EC is an extremely safe connection with zero failure. With
You understood, right? The whole process, starting from the starting from the casting of the facing walls, how these facing panels are actually made, then from the leveling pad, over the leveling pad we start putting the facing walls, and then we start putting the reinforcement, filling the soil, compacting it, then again filling the soil, compacting it, like that we construct the whole wall. Also we need to take care of the proper drainage using geocomposite. We need to put geocomposite so that the water is able to drain out to the bottom. Okay, that also we have to take care. Okay, so this is the whole complete process of construction of reinforced soil wall. You will see one. You can see one interesting thing. You can see one interesting thing that we are always calling it reinforced soil wall and not reinforced earth wall. So actually that is because the reinforced earth wall term was already patented. Okay, reinforced earth wall that is already was patented by Henry Vidal. So we in a general practice we tend to use the term reinforced soil wall. Okay. Now codes and standards. So there are various codes and standards that are available, which describe or which guide us, okay, or they give us certain what to say rules following which we need to construct these reinforced soil retaining walls. Okay, so there are many codes and design standards that are available. Two most common and widely used standards are our BS code, that is a British standard 8006, and the FHWA standard, that is the Federal Highway Administration USA, that standard. Okay, these two standards are generally used in practice. So in India there is a tendency that this British code is generally always adopted. So Indian standards, all the IS codes are almost copied from British codes only. Okay, they are 95% copied from all, like copy of the British codes. So in India there is a tendency that this BS codes are followed, but this Federal Highway FHWA codes are also widely followed. Okay, the FHWA codes that are developed by Federal Highway Administration Authority in the USA. Okay, so similarly various other codes and other guides are also there. You can see here segmental retaining walls, National Concrete Machinery Association, Then we have seismic analysis and design of retaining walls body structures by NCHRP. Okay, so these are various guidelines that are available to an engineer while he is designing a RAC wall. Okay, reinforced soil wall, RSW. Okay. Now, what are the differences? Okay, what are the basic differences between our BS code and the FHWA code? What is the basic difference? So these differences were already discussed in the class, so just I will repeat it. So the main difference in the BS code is that it does not consider the seismic action. Okay, the seismic forces it does not consider, but our FHWA manual considers the seismic loads. Also, the BS code is follows the limit state method, and our FHWA follows the lumped factor method. Okay, and then we have the vertical force. The one of the main differences between the BS code and the FHWA is that the vertical load. So when we are designing the wall, what we have to do, we have to calculate the vertical stresses at each layer. Okay, at each layer we need to calculate the vertical stresses. Now the BS code says that the vertical stress is nothing but our sigma z plus what? I'll use gamma z plus w. So gamma z is nothing but the static, whatever static weight of the soil, weight of the bacteria, weight of the soil plus the surcharge. Okay, that is given by the BS code, and the FHW actually gives our is R minus L minus twice. So RV is the total vertical load, which is combined of all the loads, like say live loads, dead loads, then you have the seismic load, everything. If you combine that, you will get the RV. That RV divided by L minus twice. So L minus twice is nothing but the total width of the reinforced wall minus the twice is the eccentricity. So this is actually the Meyerhoff's vertical stress. Okay, so that is actually preferred by the FHW. Okay, that's all. Now this electrochemical properties and all, let us not discuss here. You have already seen that in the main class lecture, so let us not repeat it again. So if these electrochemical properties are nothing but how means what kind of electrochemical properties the backfill soil should have. Okay, the properties of the soil, what property should be that you go through by yourself, is already discussed in the main class, so I won't repeat it. Now, what properties the backfill soil should have? Okay, the what properties? So, what kind of soil will you choose for a backfill? That is the question. What kind of soil will you prefer as a backfill? What kind of soil are you going to prefer for your backfill, or for the soil which you are going to reinforce? Okay, what soil will you prefer?
Fine grain soils.
Fine grain soil. Will you prefer fine grain soil?
Which
Fine grain,
there is a
fine,
classification for it also, as
yeah,
per the sieving analysis.
yeah, fine, yeah, correct. But fine grain soil you won't prefer, right? Fine grain soil means this, you have fines. Fine grain soil means cohesive C5 soils, cohesion soils which have cohesion, C5 soils. That soils we do not prefer generally. Generally prefer what? Sandy sand. We prefer sand or granular soils, right? We prefer granular soils. Why do we prefer granular soils?
Good permeability.
One. This is one of the reasons. What is the most important reason that why we consider granular soil?
Compaction.
What? No. One more. Most important. Thinking in terms of reinforced soil.
Friction between
friction.
soil and,
Yeah, there is
between soil and
strength of
reinforcement.
yeah, high phi value, right?
Yes.
They have high angle of internal friction. Inherent. So high inherent soil strength. So if you want to construct a reinforced soil wall, obviously you want that the inherently only the soil should be somewhat strong, right? So that the complete wall that you construct that is strong, obviously you will prefer granular soil which has high phi value, which has high inherent strength. So that thus our structure or the whatever earth wall we are going to construct that is strong enough, right? So we will always prefer granular soil. Okay. Also, if we have high phi, we will have high delta. Delta is nothing but the friction angle between the soil and the reinforcement, right? So that is also one more reason. Okay. And other reasons that you told, high permeability. High permeability, coefficient of permeability is high, so water can easily flow and drain out. That is one more reason. And the other reason is that they have low plasticity index. Okay, they should have low plasticity index. Okay. So these are the basic properties that the backfill should have. Now tell me this. Which friction angle should be considered when and why? So generally what we do, we do direct shear test, right? We do direct shear test, and from direct shear test of the soil we find out the friction angle of the soil, right? Okay. What is direct shear test? Do you recall what are direct shear tests? How do you do it? Can anyone please tell me? Can anyone please help me recall what are direct shear tests and how do we conduct direct shear tests?
The soil is confined in one direction where the pressure is applied from the top direction.
How do you do the direct shear test? You have a direct shear apparatus, right? Can you recall how the direct shear apparatus looks like?
Yes. Yes.
How does it? How it has two parts, the bottom, top, right? So what direct shear box? You have a box. Okay, you have a box which has a bottom half and the top half. Okay, box. So you fill the soil in this box. Fill your soil. Okay, tamp it and fill your soil in the box. And then what you do? Then you apply a constant normal load. Constant normal load you apply over the soil, and then you start applying some shear strain.
Sliding force.
So what? Yeah, shearing. You start shearing. So what is going to happen? The it is going to it is going to start shearing like this. Okay, shearing like this. So what you will get? So if you plot your shear stress versus the strain, you will get something like this, or something like this. You are going to get, isn't it? You are going
Yes.
to get something like this. Now what you do? Now for first you keep this as 10 kPa. Okay, 10 kg, so 10 kg per centimeter square. Then you do the test, you will get one graph. Then you increase it to 20 kPa. Then you will get one more graph like this. Then you will increase it to 30 kPa. Then you will get one more like this. So like this you are going to get three graphs, right? So now I have normal forces and shear force. Normal force 10, 20, 30. This normal force I have. Now corresponding to that, I will have shear stress. Now which shear stress should I take? This is for 10, 20, 30. Now which shear stress should I take? Should I take this peak or should I take this residual? Which shear stress should I take? That is the question. Now this is the question. Which shear stress to take? Either should I take the peak or should I take the residual one? Should I take the peak or should I take the residual one? Which one to take?
Peak shear stress.
Why peak shear stress? Then the question is why peak shear
So
stress?
we need to know the stress at which it fails. To know the bearing capacity till what the loading can be done. That's why.
No, see, that is not the reason. The reason is for when you construct, say, retaining wall, when you construct retaining wall, generally the strains that are generated, you want that the retaining wall should perform in low strain condition. Like you do not want that the retaining wall should have very large strain, right? The strains that will be generated in the soil, it will be very less. It will be very less. So we assume that the strain will be in the low strain, means the strains will be less. Strains will be less. That's why we take the peak values. So we take these peak values, and from there we draw this line, this data line. We have 3 points. It will pass like this. From here you can get the phi value like this. Now, say in some cases where the strain is very high, you know that the loading conditions are going to generate very large strains. Okay, very large strains. In that case, we will take the residual values. In that case, we will take the residual values for the design. Okay, else in retaining walls, very high, very big slopes, very long or very large slopes or retaining walls, generally the strains are less. That's why we consider that our operational region will be the low strain region. Low strain region, that means the whatever the friction angle that will be mobilized, that is the peak friction angle. Okay, the peak friction angle. That's why we take the peak values. That is the reason. Okay, that is the reason. And the question, if you get this question, is generally neglected. Okay, this we generally neglect the question. Why do we neglect the question in design? Why do we neglect the question? We neglect the question because it generally tends to give additional factor of safety in the problem. So we want to construct the design a retaining wall considering that the soil is a little bit lesser strength, so that we can have a little bit conservative design. That's why we neglect the question. Okay, that's why we tend to neglect the question. Okay. Okay, right? So understood. Now tell me again, what did you understand? Why do you, when do we use the peak friction angle? When do you use the peak friction angle? When do you use peak friction angle? When do you use, in what cases do you use peak friction angle? Generally for retaining walls, high retaining walls or big slopes, we consider peak friction angle in our design because we think that, or we consider that the strains that will be generated will be in the lower region. Okay, the strains that are going to get mobilized, it will be in the lower region, and that low strain, you can see that this strain actually mobilizes the peak friction. Now say you have a structure, we have a very soft soil. Over that soft soil, you are constructing, you are having a slope, or you are having a what to say, yeah, you are having some soil structure. Okay, very over a soft soil, you are having a retaining wall, say small retaining wall or a shallow slope you are having over a soft soil. Now as the base soil is soft, obviously it is going to have we assume that it's obviously going to have a large deformation. So large strains are going to get mobilized. So large strains are going to get mobilized. That's why in those cases only we consider the residual strains. Okay, else generally in the case of our steep slopes and retaining walls, we consider that low strain, these are low strain conditions, and in low strain conditions this peak friction angle will be mobilized. Okay, peak friction angle will be mobilized. Okay, now lateral earth pressure theory. So this already we solved in the first class. We solved some problems. Today also we will be solving some of the more basic problems just for revision sake of revision. So yeah, so for a soil, say soil having friction angle phi, what is the active earth pressure coefficient Ka? What is Ka? What is Ka? That's the relation I'm asking. What is the formula for Ka?
1 minus sin phi by 1 plus sin
Yeah,
phi.
1
1
plus
minus
sine pi by 1 minus sine pi.
no 1 minus sin phi by 1 plus sin phi. Kp, passive earth pressure coefficient is 1 plus sin phi by 1 minus sin phi. But I am asking about Ka. But generally, see why Ka? Generally, active case is only going to get mobilized, right? So you have the wall here, you have the soil here. So the soil will tend to move away from the backfill, away from the backfill. So there is the active case, right? Active case. That's why we are focusing on the active thing. Okay. So what is the x direction? What is the earth pressure? Ka gamma z at any depth z. So this is the, so at any depth z, k into gamma phi, these are the properties, minus twice c root over ka plus k into q. Q is nothing but the surcharge. Okay, q is nothing but the surcharge. Okay. Uh, now say you have a inclined backfill. Okay, in inclined backfill. So this is for a straight backfill, right? We have P, then P force that is acting half. So this everything you already know. We already solved some solve problems also in the previous, in the first class, first discussion session. So already you know what if the backfill is inclined, then K is cos beta minus cos square beta. Is okay. Now again one more case is also there. One more case is if say your retaining wall is not straight. It's not straight. It's inclined at some angle. It's inclined at some angle, and also you have some friction. You have some friction between the soil and the wall. In that case, you have to use the Coulomb's theory. So this comes from the Rankine's theory, right? And this in this case, the Coulomb's theory will actually give you. Okay. So we are not discussing that again and again. Yeah. Now let us come to design loads. Okay, so what are the loads that we have to consider while we design a retaining wall? What are the loads? So what is the load? First is the self weight of the soil. We have to consider the mean self weight of the soil. We have to consider, right? That is the dead weight. Then we have the live loads due to uniform surcharge, or say the car that will be traveling over that retaining wall. So generally, where are retaining walls used? Retaining these reinforced soil walls, you will generally see where these are used. These are used where? These are used in the approaches, right? Approaches of flyovers and all these things, right? These are used there. So generally over the reinforced soil, generally there is traffic that is moving. So that live load you have to consider, that load, or the surcharge load. Then you have to consider the horizontal load from the crash barrier. So you have, so I'm drawing it like this. Okay, so this is the soil wall, and again this side, again one more back to back you are constructing. Okay, this is the soil. Okay, so this part is reinforced. and here you have this your highway that is constructed. Okay, these are your facing walls, and here you have the highway. This is the median. So you have crash barrier here, crash barrier here. This is the median, and you have your 4-lane highway that is passing over it. Okay, generally this is where your reinforced soil walls are actually used. Okay, so the weight that is coming from here on this soil that you have to consider. Then from the crash barrier, so if a vehicle collides with the crash barrier, some point, some rotation or some moment, said that some load is going to come, that load you have to consider here. Okay, all those loads you have, so all those loads you have to consider. Okay, then the braking forces, say you have high speed traffic moving, so when a vehicle applies its brakes suddenly, high traction forces are generated on the pavement. That load is actually transferred to the ultimately to the soil, reinforced soil below. So all these loads actually you have to consider in your design. Okay, so I'm not writing it again and again. So these are the loads. Okay, this comes the design loads. Now comes stability calculation. Now, in the previous class, we discussed about two failure modes, right? What were those failure modes of reinforced structures, reinforced soil structures? Two failure modes were discussed in the previous class, right? What were those failure modes that we discussed?
Pull out failure and rupture failure.
What?
Pull out failure and rupture failure.
Yeah, pull out and rupture. These were the two failure modes of reinforced structures, reinforced soil structures that we studied in the previous class. Now those those failure modes will actually control the internal stability of the one. So we'll see internal stability calculation, external stability calculation. While we solve the problems, while we solve the design problems, we will see that we consider the internal stability as well as the external stability also we will consider. So that part, so the rupture failure, those failures, the pull out failure or the rupture failure, those will actually control the internal stability of the system. Okay, the internal stability of the system will be controlled by that. Now next comes the external stability. The external stability means this thing. First, say you have a retaining wall. I am just drawing line diagrams. Okay, line diagrams. You have the reinforced soil wall. So soil is pushing the wall in this direction, So the complete structure should resist the sliding, right? So here bottom you have foundation soil, right? So this whole structure should not should not say should not slide and come here, right? Okay, there the resistance force should be resistance force developed at the interface between the foundation surface and the reinforced surface should be optimum, right? So that the sliding does not happen, the wall does not slide. So fast stability is the sliding stability. Okay, so this sliding failure should not happen. This is one first external stability criteria. Okay, the sliding should not happen. Now what is the next is our overturning. Now again we have retaining wall, we have like this. So what? So there is a tendency that the horizontal load that is acting there, this might lead in the overturning of the moments might lead to the overturning of the structure. Okay, so this is the second one, the overturning stability. Now third is the bearing capacity. That means what? You have the soil here, the foundation, this foundation soil should be strong enough to take the load of the reinforced soil wall. It should not be such that the foundation soil is so weak that there is bearing capacity failure of the whole structure. Okay, so you have to consider this also, the bearing stability. Sliding. So 3 factor of safety checks we are going to make every time we design a reinforced soil wall. We are going to make three checks: sliding check, overturning check, and bearing check. Okay, so we are going to find out the sliding factor of safety, the overturning factor of safety, and the bearing capacity factor of safety. All this we are going to calculate and check. Okay. And apart from, so basically these three are the main important stability criteria. Apart from that, one more criteria is our slip circle failure that might happen. Say you have a slope, and over the slope you have your reinforced earth wall. Okay, we have the reinforced, is the base, this is the vacuum. So this is a slope. Now you should check always for slip circle failure, so that no cases should be there that a slip circle originates from here and then passes through the slope like this. So if you have to make the stability you have to do the stability calculations and check that there is no slip circle failure. So if there is a tendency, you need to reinforce the slope or whatever you need to do. So this also you need to check. So if there is a tendency for slip circle failure, what will happen? The whole see these, in these cases all this will be satisfied. All this will be satisfied, say. But if the slip circle failure is not satisfied, what will happen? The whole structure is going to come out with the slope, come out with the failure of the slope. Okay, so this also we need to consider mostly when we are constructing the reinforced soil wall on steep slopes. Okay, the slip circle failure. Okay. Now these are the various load combinations that are actually given in your BS 8006. So load combination A, B, C for various criteria is given. So I am not going. So these are various factors that are given that you have to multiply with the load, and then total load you have to calculate, and using that load you have to do the analysis. So I'm just not repeating that. We'll see that later if we need. For now though, just you can see whatever it's given here, I'm not repeating it again. Okay. Okay, now I have how many? Let me see. 1, 2, 3, 4. 4 problems I have, very easy problems. So please try to solve this now only. Each problem should take not more than 2 to 5 minutes, not more than that. Okay, the first problem is retaining wall. Very easy problem, similar to ones we solved in the first class. Okay, problems related to retaining wall only, normal retaining wall, not the earth reinforced retaining walls, reinforced soil retaining walls, normal retaining walls. So just try to solve this. Try to solve this. What is the first question? A retaining wall 6 meter high retains a cohesionless soil. Retains a cohesionless soil with an angle of internal friction 35 degree. G is equal to 2.69. N is the porosity that is given. Surface is top level with that. A water table is also given. Determine the active earth pressure per meter length of the wall. Going to solve this? How are you going to solve this? Very easy. First, see, porosity is given. So if it's almost 5, so firstly I will solve. Porosity is given. From here, void ratio I can find out. So this will come out as 0.681. All right. Then we can find out the dry unit weight. So if we do this, you will get 15.7 kilonewton per meter cube. And what will be the submerged unit weight? Will come out as 0.86. Now tell me, what is the coefficient of active earth pressure? Calculate the coefficient of active earth pressure for this. Calculate, please.
You just said 1 minus sin pi by 1 plus sin pi.
Yeah, 1 minus sin. What is the value? It is 35 degree, right? So 1 minus 35, 1 minus sin 35 by 1 plus sin 35 will be 0.271. Alright. Now next question is, our retaining wall is like this. Right? How much? It's 6 meter high. Now water table lies at a height of 2.5 meters. Right? Now we have to calculate the active earth pressure per meter length. So how will you do that? How to do this? See, in the top portion, in this portion, the soil is dry. So what will be the variation of active earth pressure? It will be something like this. Right? What is this value? 2.5 height times gamma 15.7 into Ka. This is this value. Right? Right? Now this portion, that is submerged, for this portion triangle will be something like this. In that case, what will be this one? 3.5. Done. Now one more thing also, you have to note that water is there, so water pressure will also be acting. So for water pressure, how will be the variation? It will be from below at this level. How much is this? How much is this? 9.81 gamma W into 3.5, that is the height. So you have four figures here. So just calculate the area of this 4 figures. You will get the total active earth pressure. So what is P1? Half area of the triangle, half into 2.5 into 15.7 into Ka times the height. What is the height? 2.5. So this one is going to come as 13.29 per meter. Similarly for P2, P2 is what? This one, this is a triangle. So what is the base? This length. This length is same as this one, 2.5 to 15.7 into Ka times the height. What is this height? 3.5. So this one is going to come as 37.23 per meter. Similarly, P3 is the area of this triangle and P4 is the area of this triangle. So P3 and P4 directly I will write. P3 is 16.37 and P4 is 60.08. Total P, if you calculate summation of all P's, you will get the total P as 126.99 Newton per meter. Now you know how to, now where is this PA actually acting? It is acting somewhere in the line, right? So PA is acting at some height y from the base, right? But that y we need to find out. So how to, so to find that out, we just take the moments of all these forces from the bottom. So how do you do? Y is equal to 13.3, this 13.3 times 3.5 plus 2.5 by 3 into 3.5 plus 2.5 by 3 plus 37.23 times 3.5 by 2, 3.5 by 2, half of this. Then this one, what is P3? P3 is 16.37. So 16.37 into 3.5 by 3 plus last one 60.08 times same 3.5 by 3 by total, this one will come out as 1.68 meters. Okay, so the total active earth pressure of 126.99 kilonewton per meters is acting at a height of 1.68 meter. Okay. Now one more problem. For the retaining wall shown in the figure, find the active thrust and the line of action. All the properties are given. All the properties are of the top soil. So both the soils at the top and bottom have different phi values. They have different phi values. Okay. So you need to calculate. So how to do this? So first I will find out Ka1. Ka1 is 1 minus sine 30 by 1 plus sine 30. 0.33, and Ka2 is nothing but 0.271. Alright, now what is gamma sub water table is here. Okay, so gamma submerged is going to be, gamma saturated is given 19 minus 9.81. Now for the top portion, what will be the variation? Same, triangular. What will be this? Please tell me. What is this? What is this? What is this length? What is the length of the base of this triangle at the top? This top triangle from this soil. What will be the length of this portion? What is the pressure at this level? What is the active earth pressure at this level? Please tell me. What is the active earth pressure at this level? What? Very simple. Gamma. What is gamma? 16 times height 3 meters times Ka1, isn't it? Now see the bottom soil, this K is changing. Now for the bottom soil, if I write, I can write it like so. So it will act as a surcharge. So whatever load is acting at this level, it will be acting as a surcharge for the bottom layer. You can think it that way. So for the bottom part, if you want to draw, it will be rectangular, and this will be nothing but 16 into 3 charge that is acting on the bottom into 3 into Ka2, and this 2. Done. Then again at the bottom, for the inherent soil, we will be having again same triangular variation. What will be this? 3 it is submerged, right? So 9.19 times 3 times 0.271 plus one more last thing due to water. The water is going to be how much? 3 into 9.81. So you have to somehow find the area of all these figures. So I will just directly write it down. P1 is going to be total P okay. Similarly, if you want to find the point of action, similarly we will do summation PIYY by summation PI. If we do, we will get 1.77 meters. Okay, please, I hope you understand this, right? These are very basic, how to calculate the earth pressure at all the points. We will need this later. That's why we are solving these problems. Okay. Okay, now this problem. A soil mass is retained by a smooth inclined wall of 6 meter height. The soil has a bulk unit weight of 20 kilonewton per meter cube. and an angle of internal friction of 16 degree. The top of the soil is level with the top, and whatever, leave it. Let us come directly to the figure. In the figure directly everything is given. So here the face of the wall is not straight, it's a little inclined. So what we will do is that our retaining wall is like this, right? So what we will do with this, we will get like that, A, C, B. This is the right, and this angle is 18 degrees. So we will consider it like that. Okay. Now earth pressure that is acting here in this phase you can find out. So first, for the surcharge what will it be? For the surcharge, this is one surcharge, nothing but q is q into Ka, right? And then for the soil we are going to have like this again, this 2 is nothing but Ka times 20 into height 6. Got it? And what is Ka here? 1 minus sine 16 by 1 plus sine 16, it is going to be okay. All right. Now P1 similarly will be the area of this rectangle, and P2 is the area of this triangle. So P1 will come out as Q into K times 6 is the height. So 15.33. Okay, so PA dash will be this plus this. Why PA dash I am writing, we'll see. Now see. Now like this we have made. So this is the PA dash that is acting here. Now if we combine this with the weight of this soil wedge W, which is acting downwards like this, you will get the ultimate PA. This is the final PA. Okay, so this PA we have to find out. So this W is nothing but a weight of this imaginary wedge, this wedge of soil that you are considering. Okay, so that you will find out. So PA will be nothing but square root of PA prime square plus W square. Okay, so what is W? Half into 6 into 6 tan 18 times 20 into 1, it will come out as 116.97 meter. Therefore from here PA will get us 249 km per meter, is inclined at an angle of this angle with the horizon. Okay, this angle with the horizon. Okay, so this is how we need to solve this. Okay, so again, and also you can easily find out the point of action. 15.33 times 3 plus 2. Okay, so please solve this once more again, and just see these problems once so that it's clear. Okay, and if you have any doubt you can ask me in the next class. Okay. Then the last problem we have. So this one, what I will do, a smooth vertical wall 4 meter retains a cohesive backfill soil. Now it is C5 soil with the bulk unit weight is given, angle of internal friction 0. Friction angle is 0. Now okay, friction angle is 0 degree. C is given, cohesive soil. Calculate the depth at which active earth pressure is 0, depth of tension crack, depth at which total active thrust is 0, total active thrust per unit length. Well, let us see one by one. So we have a wall like this. Okay. So generally for C5 soil, the variation of active earth pressure, you might know it is like this. Okay, so this part is in tension, this part is in tension. Okay, this part is in tension. So what, so and this height is the height at which the active thrust is 0. Earth pressure is 0, and this height, this is plus, so minus and plus are going to cancel each other. H is equal to twice z naught. This height is the depth at which total active thrust is 0. This is the point where the active pressure at that point is 0, and total earth pressure is 0 at this height. Okay, and this z naught is nothing but twice c by gamma root over ka. Okay, now in this case, what is our ka? What is our ka? C phi is 0. Phi is 0. So what is ka? If phi is 0, what is ka? What is ka if phi is 0? Phi is 0, right? Friction angle is 0. So 1 minus sine 0 by 1 plus sine 0, right? So 1. So what is z naught? 2 into 10 by 18. It is going to come as 1.11 meter. So h is twice z naught. It's going to be. Now this case is valid only when a tension cracks do not develop. Sometimes what happens, tension cracks actually develop here. Okay, in the soil backfill, tension cracks develop. If tension crack develop, what happens, this minus portion is not there, minus portion is not there. So the total earth pressure is the area of this triangle, complete triangle. Okay, now if tension cracks do not develop, means tension cracks are not there, that means this minus portion, tension portion is acting on the wall, acting on the retaining wall. In that case, is total minus and plus portion cancel each other, and the total earth pressure is given by the area of this trapezium. Now the base of this trapezium, I will write it down directly for you, gamma meter square. Okay, and this is nothing but this is 20 meters square. Okay, so we have is equal to half the area of this trapezium. I am finding out. Okay, area of this trapezium, half per meter. 1.78 you understood. So total height is 4 meter, total height is 4 meter. So 4 meter minus 2.22, this h. So this one is going to be 1.78 meter. Okay. Yeah, and this one is, I think, twice c by root over k. Yeah. Oh no, sorry, this is what am I writing? Sorry, this is twice c root over k. Okay, that's why you are getting it as 20 Newton per meter square. Then y, you can find out y is nothing but the centroid of the trapezium. The base. Okay, just try to just if you are confused, just try to see the basic soil mechanics in a basic soil mechanics book. You will understand it very easily. Okay, nothing else. That's all the basic we solved, just to revise our basic concepts of this retaining walls, and then we discussed everything. That's all. So with this we will end today's session, and already it's quite late. So the next class will be on, next discussion session will be on 18th. That is our next Sunday, same time from 3 to 5 on 18th August, 3 p.m. to 5 p.m. Okay, we will have this on 18th August. So next will be on 18th August, and after 18th August we are going to have on 20th August we will have. I will tell you in the next class why we are going to have on 20th. I will tell you. Okay, so next class we will be having on 18th. Okay, so let us meet on 18th, and if you have any doubt, please let me know. I will try to solve your doubts. And regarding these problems also, if you have any doubt, you can ask me. So time was less, so I just completed it really fast, a little bit faster. So anyways, if you have any doubts in this, you may also ask me. But I hope that the basic concepts of this geosynthetic part is clear, right? So why what geosynthetic are, where you are using, what are the types of geosynthetics, what function is it actually, uh, uh, what function that is actually, for what function you are using what geosynthetic. Okay, all these things should be clear. And what are the steps of construction of the REO, reinforced soil walls, what are the types of reinforced soil walls, what are the types of facings that we have, all those things. So if this is clear, then slowly as the course progresses we will be starting to solve some design problems regarding retaining wall. So in the class, whatever sir solves, please solve those very carefully. And here that detail we won't be able to solve, but we will be solving some basic problems regarding the design problems, but we won't be considering seismic and all while we solve in this discussion session. But whatever sir solves considering this seismic loads and all everything, please take study those properly, and we'll see. We'll see. Okay, so if there is any doubt, please let me know. And thank you so much for attending, and with this we will end to this session. Okay, and thank you, and happy Independence Day to everyone in advance. Okay, so thank you so much for attending. See you in the next session. Okay, thank you.